All right, looks like we're live. Let's make a little bit of an announcement and start the stream. Let me pull up my Discord server. And what are we doing today? We are live on Twitch. And we are working on, just a second, C and OpenGL textures. I'm going to give the link to everyone who's interested in being linked, and ping everyone who's interested in being pinged. There we go. The stream has been officially started. So, what it's all about? It's actually very interesting. I've been browsing the internet, and I found a very interesting mathematical thing that I would like to apply to a picture or to a texture. And that's basically what inspired the today's stream. But to be able to do that, first I wanna implement the texture capabilities for the OpenGL template I worked on one of the previous stream. Right, so I have OpenGL template, which basically gets me up to speed every time I need to do an OpenGL application, right? Because, you know, writing OpenGL boilerplate from scratch is kind of pain in the ass. So I just I have a pre-made template that I can grab and start working on OpenGL. Unfortunately, it lacks the ability to work with the textures, with OpenGL textures. And in the first part of the stream, we're going to be implementing the capabilities of loading textures and displaying textures and stuff like that. And on the second part, we're going to try to apply that mathematical thing that I found today and see if it's going to do anything interesting. I don't know if it's going to do anything interesting. And in fact, that mathematical thing is not particularly applicable to pictures, right? It was not designed to be used with pictures, but I think it is doable to use it with pictures, and I'm just curious how it's going to look like. I didn't do that before the stream, so I don't know what's going to be the result myself. So, but we're going to start with implementing the texture capabilities. So let's go ahead and do that. Hello everyone, welcome. So you can find the source code for the OpenGL template in the description if you're watching on YouTube, and if you're watching live, I'm gonna quick paste this thing in the chat. Okay, so let's go ahead and do that. I'm gonna do TeamUX, and let me switch some windows and stuff like that. OpenGL. So I worked on this template off screen, so I'm pretty sure there's some things in here. There are some things, so let me fetch this stuff from origin. And I'm gonna merge all of that like this. So let's recompile everything. And if I try to run this entire thing, this is how it looks like. So this is like a basic, you know, demonstrations of the OpenGL template. So let me see how can I implement the texture support. First of all, we need to come up with the texture that we're going to be loading into the OpenGL application, right? So I'm not really sure what's going to be the texture. So probably I'm going to grab some sort of like a Tsodin emote. Right, so that kind of makes sense on the Tsodin channel to grab a Tsodin emote. So let me see. So maybe something like Tsodin flushed. Yes, that sounds about right. I think I'm gonna just grab the Tsodin flushed and just copy paste it in here. So this is gonna be wget. So I probably have to also give it a name, Tsodin flushed PNG. Right, so here's the Tsodin flushed, and let me see. So here it is. So the encoding is probably horrible because of the background and stuff like that. I really apologize for that. So okay. So I think I already have Emacs started. I don't know why I started it twice. So let me actually put it in here. So here's the Tsodin flushed, but before we can even, you know, create an OpenGL texture out of this entire thing, we need to be able to load it into the CPU memory. So, and that means we also need to parse the PNG file. So we're going to use like a third-party dependency to do that. And we're going to be using the STB libraries, right? So if you never heard about the STB libraries, I really recommend check them out. I'm going to put that thing in the chat and also in the description for anyone who's interested. STB libraries, right? So this is the thing that we're going to use for loading the image, and specifically we're going to be using stb image one. All right, so it's taking some time. So this is the raw version of this thing, and I'm going to just download this entire stuff. So I'm going to put it in here. Okay. So now let me go ahead and simply include stb image.h, and I'm going to define stb image implementation. Right, so essentially the reason why I do that is because stb libraries are header-only libraries. That means that they act both as header and a C file, but if you just include them, they act like header files, so that means they don't include the implementations. To instruct the file to act also as an implementation, you have to define this macro in here. So, and the reason why you have to do that is because you now have control over how this particular file is going to behave. Is it going to behave like a header, or is it going to behave like a C file? Right, you can decide. In our case, I wanted to behave like a C file. I wanted to include all of the necessary implementations and stuff like that. So let's go into the main function, right? So, and this is where we probably want to load the entire file, I presume. So the question is where exactly I want to load it. Maybe before even initializing GLFW, I think that would make sense. So let's go ahead and do that, but I don't quite remember how to use this library. So it has to be something like stbi load. There we go, that makes sense. So that's basically how we use that stuff. Okay, so this is the size, and this is the amount of components. I didn't think I care about specific amount of components of that image in here, right? Because I'm going to instruct it to convert it to 4 components, right? So it doesn't really matter what's inside of the file. I want to have 4 components in here. And this thing, X and Y, do I want to keep it X and Y? Let's actually keep it X and Y. Const char file name is going to be equal to flushed, right? So let's put it in here. So this is flushed. And if data equal to null, that means we couldn't load that image. We're going to print something like error, could not load image. I'm going to provide this thing. And I wonder if error no is actually set to describe the actual error that happened there. I hope it is, right? We can always test that. So error no, right? And then it's going to be exit to 1. There we go. Cool. All right, so let me try to recompile the entire thing. Okay, and then I'm gonna also run it right away. Okay, seems to be working, though it doesn't really say anything. So what if I try to like load something that doesn't exist, right? So is it gonna throw a proper error? Emacs is so slow. Okay, there we go. Okay, could not load and no such file or directory. So it says precisely what I would expect it to say, but I forgot the new line in here. Cool. So we have a file in the memory, right? We sort of do have a file in the memory, and we need to turn it into an OpenGL texture. So the question is, how do you do that? I think you first have to generate the OpenGL texture, something like gl gen texture, right? So I think there should be some sort of a tutorial in here that we can copy paste from, and yeah, so that looks about right. So we have to first generate the texture, then we have to bind the texture, define a bunch of parameters of how to interpolate things and like different filters and whatnot. And then we're uploading the texture data into the OpenGL texture. And here they are binding it for whatever reason. I don't know why. And I guess that is basically it, right? It's going to be basically associated with like zeros texture unit. I think this is the term of OpenGL. There is some sort of like texture unit that the texture is associated with, and we'll be able to use it inside of a shader. That's precisely what I wanted here. So let's go ahead and do that, I suppose. So, and I can do that after I initialized everything. So here we are loading extensions, then we initializing the renderer though, right? We're initializing the renderer, and I'm thinking, should it be part of the renderer? Probably not right now, not right now. We don't really have that much of the texture related code developed yet to make it part of the renderer. So I think I'm gonna just like slap some code on top of existing code base and see how it like fits there. Yeah, so I'm not going to try to do anything fancy right away because it's never ends well. It never ends well. You generally want the code to sort of emerge the architecture for you. So here we're going to have something like texture, and we'll have to do gen texture in here. So we generated the texture. And after that, we'll need to map that texture like so. Right, there we go. So it's going to be 2D texture. We're working with 2D. And now we have to set up some filters. They're using linear and stuff like that. Do I want to change anything in here? Probably not. If I'll need to change anything in here, I'll just do that later, right? So the goal right now is to just make something. And the next thing we need to do, we need to upload the data to the GPU, right? That's what we need to do. Okay, so let's go ahead and do that. There we go. So the target is GL texture 2D. So what's the level? I think level, if I remember correctly, is basically meep map level. Okay, so we don't really care about meep maps right now, so it's going to be 0 essentially. So internal format specifies the number of core components in the texture must be one of the following. Can I specify RGBA32? Because that's exactly how I loaded this entire thing. RGBA32, RGBA. Okay. Symbolic constants. What if I just say RGBA? Can I just say RGBA? Specify the number of code in the texture must be one of the following symbolic constants. Okay, so if I take a look at this tutorial, what do they just use RGBA, but in the documentation they don't say that you can use just RGBA. At least I don't see that. Okay, if they say I can use that, I think I can just gonna go ahead and just use that. RGBA. Okay, so since we're initializing textures in here, maybe it also makes sense to load the texture in the same place. Right, so a little bit closer. That would make sense, I think. Alright, so here's the texture. So we already have a variable that holds the texture ID. So maybe I'm going to rename some of these things to like prefix them with texture, right? So this is going to be texture file name. Right, so texture file name, and this is going to be texture width and texture height. Texture width and texture height. Right, texture width and texture height. Cool. So then I will be able to just use texture width and texture height in this specific function, right? Texture width and height. So the border can be 0, it doesn't matter. So what about the format? The format specifies the format of the pixel. So I suppose it's going to be just RGBA, right? RGBA. So the type, I don't quite remember. Can I just say unsigned byte? In this specific case, we use unsigned byte. Cool. And then we have to specify the data, specify the pointer to the image data in the memory. So I think I can just say data. We can call it texture pixels. I think that will make a little bit more sense, right? So texture file name, texture width and height, and texture pixels. Cool. Yesu, 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 kawaii freaking desu. Texture pixels, texture pixels. Cool. So we have everything, I think. All right, so everything is working, everything is loaded. I didn't see any errors at least. So yeah, I think we managed to load the texture. Though, do we need to do anything else? I think that is basically it. Here they try to unbind some stuff, so there's depth texture. I don't think it's important. I don't think it is important. So now from the shader point of view, we will have to create a uniform of a sampler to D, I think. Right, so that's what we have to do. Let's go to the fragment, shader, and let's create a uniform. Sampler to D, I think that's what we need to create, and this is going to be a texture. Though word texture seems to be already taken, so we probably want to do something else. So let's call it something like text, right? So short for texture, probably that makes sense. And in here, what we want to do, so we already have UV coordinates, which probably means that I can just go ahead and put one in here and do texture. Right, texture, use the texture and the UV coordinates. So though I want to actually consult the reference texture function just to know what are the arguments of the texture function. Okay, so let's take a look at this thing. So yeah, you accept the sampler and the vector. There's also some sort of a bias, but I don't really care about that. Okay, so this is the output color. So essentially we just take the coordinates and we use the color of the pixel from the texture, and that should just provide everything. Oh, there we go. First try. I first tried loading the texture. How about that? Speedrun. I speedrun this shit. So how much time did it take me? It took me 15 minutes, yes. That's a world record. That's a world record. Pretty good. Though, got cooler, probably, I don't know. So I wonder if we can do something more interesting with that. So I'm pretty sure I can just keep it like that, right? And keep modifying this entire thing. Essentially, I can go back here, right? So now it's just like displaying the colors, and then I can mix in the texture into the colors, I think. Can I just do plus? And yeah, so there is the colors and the texture behind the colors, if that makes any sense. You see, it's kind of crappy, but yeah. So seems to be working. Though we want to actually kind of invert the entire thing, so I'm gonna do it like this: UVX and UVY, and it's just gonna be minus, like 1 minus, and there we go. So everything is flipped correctly, more or less. What if I multiply this entire thing? Is it gonna be better? Multiplication is better, actually. Yeah, multiplication is way better. So yeah, that's pretty pogue. That was pretty easy. Didn't expect that. Pogue. Okay, so what I want you to do with this specific texture, So today I was browsing the Hacker News, right? And I found an interesting article. So I think the article was from the website Beat 101, yeah, letting go of random. So, and actually, like, I discovered like this website, and this website actually seems pretty cool. So I really recommend to check it out. But specifically, I'm interested in this article. Right, I'm gonna copy paste it in the chat for anyone who's interested, and of course I'm gonna put it in the description for the YouTube folks. Description MD, there we go. So letting go of random. So essentially it's a simple tutorial that talks about like different random number generators and how to generate random data that looks interesting, right? And for example, one of the first suggestions that they make on how to make everything more interesting is to not use the uniform distribution random number generator, but use the normal one, right? And when you use the normal one, the data looks a little bit more interesting, right? As you can see, so this is how it looks like. And so there's also parallel noise and whatever, you know, just a simple tutorial. And so they suggest to use something that is called What's the name? Stack Overflow trick. The Box-Miller transform. I hope I pronounced that correctly. But essentially, it's a transformation that takes the uniform distribution and turns it into a normal one. Right. So you can just have a random number generator, you put it through that transformation, and it becomes a uniform one, and this is how you get that. So let's actually implement that. I actually never confirmed if it is in fact, you know, uniform one, normal one. So let's actually write a simple program that just like samples the random number generator from C and then samples it again, but using this transformation. As you can see, this transformation is rather simple. You know, just square root, logarithms, cosine, and yeah, stuff like that. So let's just implement that in C. Okay. Box-Miller. Miller C. 2. Okay. So I probably want to also include standard library. And since they're sampling, like using JavaScript, math random, right? So math random, if I remember correctly, returns values from 0 to 1, right? In C, we don't really have such thing, but we can implement one. Random float, right? So essentially the way we're going to do that, we're going to call random, right? I'm going to call rand, and we're going to divide it by rand max. I think this is how it's called. Maybe it's max rand or rand max. If it's max rand, the compiler will complain and we're going to fix that. Then I'm going to return that, but before I return that, I want to convert everything into float. So this way we get the sort of JavaScript-ish random number generator, more or less. So let me now call this thing a couple of times. Well, 10 times to be precise. And let's do it like this. F, I just want to see the result of this thing. Rand, maybe I should just call it a rand instead of random, because, you know, the rand in here and then rand in here kind of makes sense. Am I right, fellow bike shaders? So I think I already have a makefile. Yeah, I already have a makefile. So I can do something like this. All main box Miller, right? And for the Box-Miller, I'm going to be using pretty much the same flags and the same compiler, I think. I'm not going to be using the same dependencies though, but the same compiler and the same flags do look like a good idea. Though they also add this include, which is kind of fine. I don't think it's a bad idea. So Box-Miller, Box-Miller.c. Okay. So, and in here I'm gonna just do build everything, right? So, and it built this entire thing, and I may try to go ahead and just run it. And as you can see, this is what we got. We just got the simple random number generator that generates floats, right? So the next thing I want to do, I want to just sample it like, I don't know, 1,000 or maybe 1,000,000 times and just see the distribution, if you know what I mean. Right, we may divide the range from 0 to 1 by 10, and basically each individual sample, we can round them down to like closest integer, if that makes any sense. Hopefully. I'm not sure if that makes any sense, but we'll see. So let me basically define quantization. Right, so in how many pieces we're gonna divide the range from 0 to 1. So I'm gonna call it n, and this is gonna be something like 10. And then we're going to have some sort of samples, right? So this is samples. Maybe I'm gonna call it distrib. So this is the distribution, and there we go. So n defines also a step, right? It defines a step. And that step is essentially 1 divided by n, right? So this is basically the step for each individual sort of like sample that we're rounding them down to or whatever. So now, what do? I'm going to make let's say 1,000 samples, right? I'm making 1,000 samples, and I do random float, and I want to divide it by the step, and then I'm gonna floor it, right? I'm flooring it down and turn it into an integer, and that turns it into an index that I can use within the distrib, right? Distrib. And I can increment it by 1, but first I also want to actually set it to 0. There we go. So essentially I'm collecting a histogram, right? I'm making like 1,000 samples, and I'm collecting a histogram, and also I'm using this specific resolution. Though maybe this n should have been called something like resolution, but I mean, whatever. After that, I'm going to go ahead and just like print the all of the numbers in here. So it's going to be something like this, n plus I. And in here, we're going to just print the following thing. So this is going to be f, and then we're going to have a d, how many of those things we've got. And this is going to be I multiplied by the step, right? So multiplied by the step, and the value is going to be distrib I. All right, so that should be it. That should be it. So let's try to build this entire thing, and let's try to run it. And it didn't really build anything. Circular dependency dropped. I think I did a fucky wacky somewhere. Yeah, thank you so much. Okay, Florf, we need to include the math, right? We're including the math. And then we also have to link with the math. So I wonder if we can just have something like libs and say lm and just link with these libs. Okay, so, and I would say that they are around the same, right? So 85 and 100. So if we have more samples in here, let's say like million of samples, does this look uniform to you? I would say this is pretty uniform, right? So this is like a random number generator with uniform distribution. It's as uniform as you can get it. We can increase the resolution if that's something that you guys are interested in, right? So here is the a little bit higher resolution, and it is pretty uniform. So we have a uniform random number generator. And we can apply now Box-Muller transformation to turn it into a normal one. Turn it into a normal one. Why in some functions you put void as a parameter in others don't? So sometimes I forget to put void as a parameter, so that's why. But usually if the function does not accept any arguments, I want to put a void in there in C. I already explained that multiple times, but I can explain that again. So essentially in specifically C, not C++, specifically C, there is a semantical difference between this function, right, and this function. Right. So the function that has void does not accept any arguments. It cannot accept any arguments. So, I can even demonstrate you that. So if you try to call f with 69, this program will not compile. As you can see, too many arguments for the function f. Makes sense. But if you don't provide void in here, this program will compile, which is very interesting. The question is why. In fact, you can provide as many of these arguments here as you want, and it will still compile. The thing is, in C, specifically in C, not in C++, in C++ they fixed that. In C, if you don't have any parameters in the function, this function is considered variadic, meaning that there is implicit ... in here. So, yep, that's basically the answer. So, and I put void in there usually to explicitly indicate that I don't mean a variadic function, I mean function that does not accept any arguments. And sometimes I don't put void because I forget. It's as simple as that. So, but usually, generally, if I program in C, I want to put a void in there if I mean function that doesn't accept any arguments. Does that make any sense? Hopefully. So in C++, it's not going to be a problem, by the way. So if you have main CPP, we can even confirm that. iostream main, right. And if you have function void f, and if you try to call it 69420, it's not going to compile because it's C++, and in C++ it is not allowed. So yeah, if you have a C program that depends on that feature of C, right, like implicit ... it's not going to be compilable by C++ compiler, right? C and C++ are different languages. They're semantically different, and especially syntactically different. Just another C implicit weirdness, yes. Is there any way to use those arguments? You can use them as any variadic arguments. C variadic function. I think. I actually never tried that. So usually when I used variadic functions, I explicitly put ... But I never tried to access variadic functions with implicit ... And to be fair, I don't really care that much because it's kind of outside of the scope of what I'm doing right now. All right, so let's try now apply the Box-Miller transformation. So I'm going to do the following thing. Float rand bm. Right, so this is going to be void. So how do you apply that? So you actually generate two numbers, right? But you keep generating them. You have to make sure that they're not zero for whatever reason, which is fine, I guess. So let's go ahead and do that. Excuse me. Float u 0 v. While u equal 0, we keep generating this entire thing using the uniform distribution, right? And the same goes for v, right? Which is probably never going to be like an infinite loop, right? Because after the first one, it's quite likely going to fall through, so which is fine. We're just making sure that it's never 0. After that, we take u and v. For u, we take natural logarithm. I suppose this is the natural logarithm. Then multiply by -2, and then take a square root. And then we multiply by cosine to pi of v. So that's basically the magical formula that you have to apply. And this is basically the Box-Miller transformation, right? So that's basically it. All right, so let me see. I'm gonna use... How can you have like a natural logarithm in C? C math. I would like to have a CPP reference, please. Can I have CPP reference? That would be kind of nice. Log. Natural. Okay, so it's just log. All right. For some reason I thought maybe it's ln, but it is in fact log. So this is gonna be, so do we have to provide f? Yes, so if I mean float, I probably want to provide f. So this is a square root, so then cosine to f. I'm not sure if we have pi. I think we don't have pi, so that means I'll have to define it somewhere. Give me pi. Okay, so is that it? That seems like it. Oh, this is not what I'm trying to do. Okay, so everything seems to be working, but now I actually would like to visualize, you know, the normal distribution is actually quite spectacular, right? Because it's a parabola, some sort of like it's a parabola. And I would like to see that parabola, if you know what I mean, right? So maybe what we want to do in here, we want to sort of, you know, render this as a histogram, right? So basically each individual number is going to be for each individual number, we have a corresponding like a bunch of stars in there, you know, the usual stuff people usually draw in the terminal. So yeah, let's try to do that. Kind of interesting. What is going on in here? So here's the compilation of our nation. So let's remove the CPP stuff. It doesn't matter. None of that has anything to do with what I'm doing right now. All right, so how are we gonna display the histogram? The first thing I want to do, I probably want to find the maximum value, because everything is going to be rendered to like a relative to the maximum value. So let's define something like int max max value, and since it's an integer, I probably can put -1 in here. Let's iterate through the entire histogram. N plus I, right, and oh boy, if max value is less than distrib I, I'm going to assign max value to distrib I. There we go. So now I have a maximum value. Then, as I render everything, I can take the current distribution and divide it by the maximum value, right? And that basically means I have a percentage of the bar that I'm about to render. But the question is, what's the size of the bar that I'm about to render? So let's define something like bar length. Let's say that the bar is going to be, 10 characters, right? So here's the distribution, and all of that is integers, so that means I want to actually convert them to floats, right? So this is going to be floats, and that's basically the percentage, which I want to multiply by the bar length. And this basically gives me the amount of characters I have to draw. In fact, to get the amount of characters, I need to floor it and then convert it to an integer. And that will give me the amount of characters I need to draw, right? After that, I'm pretty sure I'll be able to just do that. So, so this is that. And then I can probably do something very, very cheap, right? Super cheap. So this is gonna be space. I'm gonna draw everything character by character, because I don't remember how you do that with the printfs and stuff. So put C, and the character I want to draw is this one, actually not N, but M, yeah. Std out, and then we're gonna put the new line in here. So this is the std out. So that should draw the like actual histogram, hopefully. We'll see how it goes. Okay, so since it's a uniform distribution, as you can see, it is pretty uniform, like only one thing stands out, which is exactly 10 characters, and it's probably maximum. And I can always just make it a little bit bigger. I can say that maybe it's a 20 characters, who knows? So as you can see, I can control all of this stuff. So now, if I replace the regular random with random BM, is it going to be uniform? It's actually segfaulted. Which is rather interesting, and I think I know why it's segfaulted. Because rand BM is probably not between 0 and 1. So that could be a thing. Let's go ahead and actually confirm that. I'm going to return 0, and here I'm going to just like sample the rand BM to confirm this entire thing. Let's say we're going to sample 10 values. And we'll see what we can do with that. We'll see what we can do. Rand BM. Okay, it is not. And the question is like, what's the maximum and minimum value between them? We can always map that to 0, 1, you know what I mean? Like, we can always map that. Alright, so let me actually do like maybe thousands of them. We can always just run million of these simulations and see like, the range between those things. Okay, float minimum. Float max, I don't remember how this constant is called, and maximum is going to be float min, and essentially in here, this is the sample, rand BM, and if minimum is greater than s, minimum becomes equals to s, and if the maximum is less than s, maximum becomes s. And then we want to print all of these things, right? So this is going to be min. Float mn and max is gonna be mx. So let's find out if I was right. So it's not float mx. Alright, so it's somewhere in the limits. Somewhere in the limits. C. Limit. Where are the headers though? C limits. This is annoying. Float C float max. It's inside of float.h. Really? FLT. Okay, so it's FLT max and it's inside of float h. Okay, I'm fine with that. I didn't know that. Who would have thought? I never actually included limits though. Okay, so that's basically where they are around, right? So this is the minimum and maximum. But we did only 1,000 samples. What about million samples? Huh. Alright, so it's like around -5. Which is kind of sus. Is it even bounded? I feel like it's not particularly bounded. If you know what I mean. What's the actual bound in there? We can just basically take 6. Also, we never see this entire thing. It's rand time 0. We never actually see them. Okay. So maybe can we just basically ignore the things that are outside of a certain range? We can try. Because I feel like it's unbounded. I think it's unbounded. Let me take a look. Where is the article? Where is the article? Did I already close it? So box Miller transformation. Yeah. Oh, it is unbounded. Okay. So one thing we can do probably, we can simply just repeat the sample several times until we find the one that we're interested in particular range, probably. So yeah, I'm not sure how good of an idea that is. Maybe that will mess up the distribution. It will probably quite likely mess up the distribution. So, but we'll notice that. We'll notice that on histogram. Anyway, so I'm gonna do something like this: float x rand bm, and while x maybe even equal, and x like this, not. We can keep doing this stuff, and then we're gonna just do it like that. Okay, cool. Now, let's give it a try. Huh. Ooh, that's pretty cool. Huh. So it does look like a normal one, but it seems to be peaking at 0, if you know what I mean. So let's actually put the range somewhere like between -6 and 6, right? And then let's try to map that range to 0, 1. So let me try to do that. So I have to add 6 to this entire thing, and then I will have to divide it by 12. Right. So I think that's the thing we want to do in here. And this is a normal distribution. How about that? So that didn't really mess up the distribution that much. Right. So that didn't mess it up too much. It's pretty cool. I like that. So we can change that range a little bit, like -3, 3. So that will probably spread it a little bit, but it didn't spread it that much. Oh, okay. So we can actually define this range as the constants, right? It probably makes sense. BM range, and let's say it's going to be 3F, and here we can just do BM range, right? This one becomes BM range divided by 2 BM range. There we go. Cool. So yeah, so this is basically the distribution. Cool. So we confirmed that it does actually produce the normal distribution, so which is kind of cool. But now here is the interesting thing. So if I take a look at the Wikipedia for this specific transformation, this is actually something interesting. So I'm gonna give the link to this thing in the description and also in the chat. So let me see. So the description, where's my description? So Box-Miller transform. So the way you do the transformation, in fact, according to the Wikipedia article, you're supposed to take 2 independent samples, and that's precisely what we did in here, right? So if we take a look in here, we took 2 independent samples, and then you can produce 2 other independent samples. So U1 and U2 are 2 samples from uniform distributions, and you can turn them into 2 samples with the normal distribution. Right, so you take 2 samples and you get another 2 samples. But in this specific example, in that specific article, they basically threw away the second value and only used the single value, right? Because they only need the single one. But the fact that this thing can produce 2 independent normal standard distribution values actually gave me an idea. What we're doing in here, in fact, we're mapping 2D coordinates from one space to another space. And that's effectively what this entire thing is doing. Right, you have a 2D coordinate and you literally mapping it to a different space. And in fact, there's a pretty cool SVG file in here that demonstrates that. So let me actually show you. So they show that here is the 2D coordinates of the 2 samples, and the second point in here is basically the place where it's mapped by the Box-Miller transformation. Right. So that's basically what it does. It maps one space to another space. You see where I'm going with that? You see where I'm going with that? What if we use this thing that is designed to map the distributions and apply it to a texture? What if instead of using random numbers, we're going to use the pixels of the texture and we're going to map them to a different place and see how that will distort the texture? You see what I'm doing? I think this is cool. I think this is an interesting idea. So how exactly is it going to distort? Because this thing is not designed to like transform any images or anything like that, but it feels like it could, right? It feels like you can use that to transform images. And it's super easy to implement that using the, the shaders, right? So let's go ahead and do that. And that's precisely why I started today's stream, right? I started to look into that and I thought, like, that's a pretty cool idea. I want to see that. All right. What the fuck is going on? My neighbors are also thinking that it's a good idea. All right. So I'm going to rebuild the entire thing. And I'm going to start this entire stuff. All right. So right in your face. I'm flashing right in your face. So, and let me just put this into all right, so this is going to be the fragment stuff. And how are we doing all of that? So here are the UV coordinates, so we probably want to transform them first. I wonder if I can copy paste that stuff in a more convenient way. Right, so can I split the entire thing? I'm gonna just move this stuff in here. There we go. That's pretty convenient. So that's why I'm using Titan Window Manager. So Z0. And there's something called R in here, but I'm not sure what exactly is R. So we're gonna use square root. So square root doesn't exist. -2 multiplied by log. Log does exist as well. And this is going to be UVX, right? UVX, hopefully. Didn't make any mistakes. Okay, cool. Multiply by cosine 2 pi UVY. Which is rather interesting, right? So they say that Z0 and Z1 are independent samples, but they are produced from two other independent samples, which make them kind of dependent on each other. But I'm not a mathematician, I don't really know how exactly it works, but they say that they are independent. So maybe it depends on the definition of independent. I'm not really sure what's the definition of that thing. So, and the only difference between like these two samples is that we use sign in here, right? So we just use the sign in here. And as I already know, the range can be quite big, right? So we'll have to map it as we mapped it in the C program. So let me see. See. Might as well actually define also BM range in here. GLSL does support the preprocessor, so it's totally fine. So we can also cut out anything that is outside of that range as well. Right, so if we accidentally get something outside of that range, that's going to be totally fine. Oh boy, so I'm not sure how to call that. So let's call it X and Y, right? If BM range less or equal than X, and X is less than BM range, so that's the first condition in here. I suppose the second one is going to be on Y. So I'm going to put Y in here. So that's the Y. That's the Y. Then, let me see. I want to basically map both of them, right? So it's going to be plus BM range, and then I'm gonna divide it by 2 multiplied by BM range, and I have to do that for both of them, X and Y. So this is gonna be X and this is gonna be Y. And the question is, how are we gonna approach all of that? So do I want to do the following thing? What exactly do I want to do in here? I think I'm going to remove this stuff for now, like so. So we're gonna just use only the colors, right? So we're only gonna use the colors and see how they're affected in here. So, and if it's something else in here, we're gonna use maybe a different color, right? So we can try to do it like that. Okay, so this is the semicolons. I just don't want to lose this code, because that code is very useful for like coloring things. Oh, by the way, it also depends on the mouse, so we can actually clearly see that. It's pretty cool. I forgot that I actually, yeah, I included mouse in here. All right, so that looks okay, hopefully. So do I have the compilation? Let's try to reload this entire thing. Okay, so it didn't compile. Let's find out why. Pi is undeclared. Really? You don't have pi in GLSL? GLSL pi. Let me take a look. Okay. I mean, it's not that big of a deal. Fine. Where is my pi? My pi. Can always define it in here somewhere. Also, I probably didn't want to do it like that. Really didn't want to do it. Okay. So what's the next errors? Oh, yeah, of course. Huh. That didn't change it much. honestly. Which is quite surprising, like what the fuck. So it only created this kind of like unknown things. Huh. Maybe I missed something. Maybe I missed something. So X and Y and some other stuff. So UV coordinates are like X. Oh, I see. I see, it makes sense. So that's actually quite important. I'm not gonna do -1 for now. So the there we go. That's the culmination of today's stream, everyone. That's the culmination of today's stream. Are you guys happy? Because that's what you get. So essentially, okay, I have a couple of other ideas, but yeah. We can assign maybe like a black color in here. So that should be fine. We can also do something like this, like -1. Yep, it just like flips it around, but I don't think it matters, right? When it's so cursed. So I don't think it matters that much. Also, we can do something like this. And it didn't really work because, yeah. Yeah, it applies the colors, but they're not applied according to the UV coordinates, to the new UV coordinates, if that makes any sense. But maybe they don't really matter. So, for now, I'm gonna just get rid of that. Does not matter, because I have a pretty cool idea. I do have a very cool idea. Color, and let's say vec4 0. Right, so now we're not gonna have any cursed shit in here. Everything's gonna be fine. So if we take a closer look at the transformation of our nation, we may notice, right, that we have a 2π in here, right? We have a 2π. And this is an angle. What if we change that angle? Who said that it has to be 2π? What if we say it's gonna be pi? You see where I'm going with that? All right, so let's say that it's gonna be just single pi, and okay, so it is slightly different. And the question is, what if we use time as that angle? So over time, it becomes more and more cursed, which is rather interesting, isn't it? So there's more ripples in here. If you take a look at here, there's like more and more ripples. That is fascinating. So what if we don't use time, but use just this thing again? So, and then we can use something like this. Okay, so what if we oscillate between 0 and 2π? Right, can we do something like that? I think we can try to do something like that. Because the bigger this angle, the more like a ripple should become. So we probably want to actually oscillate like within this thing and just see how it keeps transforming and whatnot. Okay, so maybe I'm gonna put some sort of like t in here, and that t is essentially so it's gonna be a sine of the time. So in sine of the time goes from -1 to 1. We want to map it to 0, 2 and divide it by 2. So that way we have a thing from 0 to 1 and back. Then we can take this entire thing and multiply it by 2π, right? We multiply it by 2π and like it kind of like cancels out. So that means I can just multiply it by pi. and something went wrong. I know exactly what, but not really. So let's take a look at the compilation error. So what's going on in here? T redeclared. T is already... Oh, okay, so T is already redeclared. Let's call it A then. So... Okay, so this is basically what I wanted to see. Yeah. So when you change this angle, this is basically what's happening in here. I was hoping that it's gonna maybe... So it only sort of changes the scale, if you know what I mean. It only sort of changes the scale. Can we change some other parameters? For instance, these two. Right. Let's put it like this. What if I say it's 2 pi? So that will not modify it, so it's fixed. And now, what if I change this parameter? Okay, it squashes it along that axis. Okay, so one... That's very interesting, actually. So the smaller this thing becomes, the more squashed to the right. Okay, so what if I make it like 5? Alright, so I suppose it will become more sort of ripple-ish. That's very interesting. Okay, so this one is sort of like 2. So this was the original thing in here. Okay, so and here we can do something like B, where we do a similar thing. Right, where we do a similar thing. Wait, what if I make it positive? So this is -2. Right, so this is something like that. But what if it's positive? It's invisible completely. Very interesting. So it only works for negative things. Okay, so I'll keep that in mind. So it only works for negative. Okay, -2. And let's do the following thing. So this is divided by 2. So this is sort of like the parameter that we use, k, and multiplied by k. So there we go. So over time, we're going to change both of the parameters. So we are, in fact, changing both of the parameters. All right. So, that's very interesting nonetheless. So this is what happens with an image if you apply a Box-Muller transformation to it. Nothing particularly interesting, but fascinating nonetheless. Right, if you basically treat that transformation as mapping from one space to another, this is how it will look like. Yeah, and you can try to control these parameters, and this is what the parameters do. We can try to, like, not map this thing to 0 and 1 and just let it be sine time and see if it's going to produce anything more interesting. Right. So, okay, so it just like goes over the moon, so it doesn't really do anything particularly interesting. All right, so yeah, does anyone have any questions maybe? You can add coefficient inside of log. Maybe. I'm not sure if it's going to be that useful. Let me see. So first let's go back to 0, 1 situation. And if I add coefficient, let's say 2 to this thing, it just cuts it. Oh yeah, so that was actually pretty useful. So now I have a capability to load textures in the template. So I think I'm gonna actually commit it a little bit later, but I will need to clean up some things. And do you guys need the Box-Muller, you know, distribution calculator? this thing that just computes this thing. I think it's pretty cool. I can upload it to Gist for anyone who's interested, so I'm gonna just do something like this. So this is a box Muller. Here's that. And yep. I'm gonna put it in here. So I'm gonna create a secret gist. And I'm gonna paste it in here. And also, I'm gonna put it in the description. Distribution calculator. Right, there we go. So it's a very simple one. All right. Int 82. Okay, Int 82. Thank you so much for 4 months of tier 1 subscription. Thank you, thank you, thank you. And welcome to our epic OpenGL club. What's going on? All right. I see what's going on. Thank you so much for telling me. All right. So. Okay, I guess that's it for today. That was a fun little experiment we did. Thanks everyone who's watching me right now. I really appreciate that. Have a good one, and I see you on the next Zosin session. About that. And let's maybe rate somebody, I don't know. Is anyone streaming anything epic on the software section? Okay, Twitch just takes too much time. I'm sorry. I don't have a patience to wait for Twitch. All right, see you all next time. Love you all.